Before a locomotive becomes a legend, it has to win an argument with steel. Not just the steel in its own frame. With the two narrow rails underneath it, every pound of weight, every piston stroke, every blast of steam, every diesel rumble has to pass through one tiny contact point where metal bites metal. Push too little power, and the train stalls. Push too much, and the machine starts bullying the railroad itself. One locomotive in this list moved so fast that a helicopter filming it reportedly could not keep up. Another carried 25,000 gallons of water and 70 tons of coal just to feed its own fire. One Soviet experiment had 14 driving wheels and still lost to ordinary track curves, and the final machine weighed more than 1.2 million pounds fully loaded. These are not museum toys. Some pushed speed. Some pushed survival. Some pushed freight power. Some pushed engineering too far and paid for it. This is MEGAMASS. 9 locomotives built with too much steel, too much ambition, and too much mechanical force to be treated like ordinary trains. The first machine does not open this list with brute weight. It opens with speed. Hungary built the MAV 242.001 in 1936 to prove that a passenger locomotive could be fast, smooth, and ahead of its time. Only one unit was ever made, and that single machine carried a specific message. Steam could still look refined while moving with serious violence underneath. Its high-pressure steam engine produced 2,300 horsepower and pushed the locomotive up to 94 miles per hour, or 152 kilometers per hour. For a 1930s steam locomotive, that was not casual speed. That was Hungary sending pressure, heat, and national pride down the rail fast enough to embarrass older designs. The MAV 242.001 used 4 cylinders, an uncommon setup that gave it smoother, steadier power. At high speed, every vibration matters. Wheels, rods, frame, and suspension all have to behave, because one unstable machine at 94 miles per hour is no longer elegant. It is a steel hazard with passengers behind it. Visually, it looked almost futuristic. Deep blue paint, silver accents, aerodynamic bodywork, an enclosed cab, and oval windows. It did not need a wall of black smoke to look serious. Its threat was cleaner than that. It broke regional speed records and outperformed locomotives from Germany and Italy. Not size, not weight, precision. A rare Hungarian locomotive proving that rail power can arrive dressed in blue and silver and still make everything else look slow. Norfolk and Western 611 did not just look fast. It made people chase it. Built in Roanoke, Virginia, and launched in 1950 as part of the Class J series, the 611 became one of America's most famous passenger steam locomotives. It earned the nickname Queen of Steam. But do not mistake elegance for softness. This machine had a high-pressure boiler producing 5,100 horsepower. That power allowed it to cruise at 87 miles per hour, or 140 kilometers per hour, while pulling a full passenger load. That detail matters. A locomotive running fast by itself is one thing. A locomotive dragging passengers, water, coal, frame weight, and pressure at that speed is something else entirely. The 611 used 3 cylinders to distribute power smoothly. Its suspension was tuned for fast, steady travel. Passengers remembered the ride as unusually smooth, which sounds comfortable until you imagine what was happening below the floor. Steel rods flashing, pistons hammering, steam pushing through the system. Thousands of moving parts trying to stay disciplined at speed. The 611's real talent was making mechanical violence feel polished. It looked built for the camera. Black body, red striping, bullet nose, and a clean profile that looked more like a weapon than an antique. Then came the detail that made it legendary. During a documentary shoot in the 1980s, the locomotive reportedly had to slow down because the helicopter filming it could not keep up. That is not marketing. That is a steam locomotive making the camera crew work harder. Most preserved machines sit still and wait to be admired. The 611 came back from retirement and still had enough pace to embarrass the sky. Speed does not solve every railroad problem. Sometimes the enemy is water. Steam locomotives are thirsty machines. They burn fuel, boil water, create pressure, and turn that pressure into motion. But in the desert, water is not a detail. Water is the entire problem. That is why the South African Railways Class 25 exists. Introduced in 1953, the Class 25 was built for dry, punishing regions of South Africa, where ordinary steam locomotives could become stranded by their own appetite. Developed through a collaboration between the North British Locomotive Company and Henschel and Son, it used a condensing tender. Instead of throwing used steam into the air, the system recycled steam back into water, extending the locomotive's range where refueling points were rare. That was not a small upgrade. That was survival equipment. The Class 25 ran with two 23-inch cylinders working at 210 pounds per square inch and produced around 4,200 horsepower. It weighed over 210 tons with reinforced suspension built to keep that mass stable on heat-punished track. Picture it moving through open desert, dark steam engine, long condensing tender stretched behind it, recycling what other machines would waste. It had a deep, steady growl, less like an express train and more like a moving factory refusing to quit. The Class 25 pushed rail power by surviving a landscape that wanted steam to fail. In the desert, horsepower means nothing if the boiler runs dry. Santa Fe 5000 was built during the Great Depression. That alone gives the machine a harder mood. This was not a decorative showpiece. It was a freight locomotive built in 1930 by Baldwin Locomotive Works, when heavy work still had to move, even while the country was bleeding money. Its nickname was Madam Queen. The name sounds elegant. The machine was not. The Santa Fe 5000 used a 210 four-wheel configuration, which meant 10 driving wheels. In freight service, driving wheels are where power becomes grip. 10 drivers spread the force into the rail and helped the locomotive bite instead of slip when heavy freight met the hard terrain of New Mexico and Arizona. Madam Queen operated at 300 pounds per square inch, used two massive cylinders, and produced around 5,600 horsepower. The locomotive itself weighed over 500,000 pounds. 500,000 pounds of black steel on rails, pulling heavy freight through mountain grades and still capable of 68 miles per hour or 110 kilometers per hour when fully loaded. That is not normal freight service. That is a railroad throwing a heavyweight at the problem and telling the grade to lose. The design was exposed, black, and industrial. You saw the boiler, you saw the wheels, you saw the rods. Nothing was hidden, nothing was softened. Madam Queen was never mass-produced, but it did not need an army of copies. One machine was enough to prove the point. Enough winners. Now look at a machine that became famous because it failed. The Soviet AA-20-1 was built in 1934 by Kolomna Works, with one huge ambition: replace multiple locomotives with one superpowered machine. On paper, it sounded efficient. One locomotive, one crew, one giant machine doing the work of several. But paper does not have curves. Railroads do. The AA-20-1 used a 3-cylinder engine and a 414 four-wheel configuration. 14 driving wheels. That number is the whole story. 14 drivers meant more contact, more grip, and more theoretical pulling power. But it also meant the locomotive became extremely long, rigid, and difficult to run through normal track geometry. It produced roughly 4,000 horsepower, but horsepower was not the problem. The body was. The boiler was so large that maintenance crews struggled to reach key internal components. The frames stretched so far that standard track curves became a serious obstacle. During testing, the locomotive often derailed unless temporary reinforcement rails were added. That is where ambition gets humiliating. A locomotive designed to replace multiple engines needed the railroad to be temporarily modified just so it could behave. It weighed over 260 tons and looked almost alien, long, heavy, awkward, like a steel centipede with a smokestack. The AA-20-1 was not weak. It was worse. It was too much machine in the wrong shape. After limited trials, it was retired and eventually dismantled. The AA-20-1 was defeated by geometry. That is why it belongs in the middle of this list. It reminds you that bigger is not automatically better. More wheels do not always mean more success. Sometimes more ambition just creates an expensive headache with a boiler attached. The next machine learned the lesson. If a giant cannot survive the curves, do not force the track to surrender. Build the giant so it can bend. Union Pacific Challenger. 3985 was built in 1943 by the American Locomotive Company for the American West, where long freight trains had to climb steep mountain grades without turning every trip into a slow, mechanical argument. The key was articulation. Its 4-6-6-4 wheel arrangement gave the locomotive two powered engine sets under one body. That let it spread power across the rails while still handling curves that would punish a rigid giant. This is the difference between overbuilt and well-built. The AA-20-1 fought the railroad. The Challenger worked with it. 4 cylinders powered the 2 drive sets, producing more than 5,600 horsepower. The locomotive weighed nearly 270 tons and could maintain speeds up to 68 miles per hour or 110 kilometers per hour while hauling heavy loads. Heavy freight needs strength. Mountain routes need traction. Curves need flexibility. Long service needs durability. The 3985 had to deliver all 4. After retirement, it was restored in the 1980s and used for special excursion runs. Rail fans traveled to hear the deep exhaust beat, watch the rods work, and see 1943 steam technology turn pressure and fire into motion again. On one famous run, it covered over 1,200 miles in a single week without a single mechanical failure. That is the flex. Not just size, reliability. A huge locomotive that can actually do the job is more dangerous than a larger one that cannot survive the route. And then, the sound changes. Forget the whistle. Forget the rods. Forget the breathing violence of steam. The next machine arrives as a yellow wall with 2 V16 diesel engines inside it. The EMDDDA-40X Centennial was built in 1969 by the Electromotive Division of General Motors to celebrate 100 years of the Transcontinental Railroad. But this was not just a ceremonial machine. It became the largest and most powerful diesel-electric locomotive ever built. The DDA-40X produced 6,600 horsepower from 2 V16 diesel engines mounted inside a single extended frame. 2 V16 engines, 1 body, 8 axles. A long Union Pacific machine, painted yellow and red, moving through the American West like an industrial warning sign. This was not the romance of steam. This was diesel concentration. Each engine powered one half of the locomotive, effectively making the DDA-40X feel like two locomotives fused into one steel shell. Its electrical transmission system delivered smooth power and strong traction for long-distance freight. Despite weighing around 270 tons, the Centennial could reach up to 90 miles per hour or 145 kilometers per hour. Your brain expects something this large to feel slow. The DDA-40X did not agree. It reset the video visually and sonically. No open rods flashing in the sun. No plume of steam breathing from the stack. Just a deep diesel rumble from two engines buried inside a long yellow frame. Several units stayed active into the 1980s. And in one strange twist, NASA once used a DDA-40X frame for vibration testing because of its strength and durability. That is not normal retirement behavior. That is a freight machine whose bones were useful beyond railroading. After the diesel interruption, steam comes back heavy, coal heavy, track punishing heavy, 7,500 horsepower. That is the number that introduces the Allegheny H8. Built in 1941 by Lima Locomotive Works for the Chesapeake and Ohio Railway, the H8 was made for Appalachian coal country, where heavy trains met grades that could make smaller locomotives crawl. The Allegheny used a 2666 articulated configuration with 4 cylinders driving one of the most powerful steam locomotives ever built. Its job was simple: haul some of the heaviest coal trains ever assembled. Fully loaded with its tender, the H8 topped 850,000 pounds, or 386 tons. The tender alone carried 25,000 gallons of water and 70 tons of coal. That tender was not an accessory. It was the locomotive's stomach. A rolling supply pile dragged through the mountains so the engine could keep feeding itself while doing work smaller machines could not handle alone. And the H8 was not slow for its size. It could reach 60 miles per hour, or 96 kilometers per hour, fast enough for wartime freight schedules. When it ran, it sounded less like a passenger train and more like a factory with wheels. The exhaust hit in heavy beats. The pistons worked like industrial hammers. The machine looked like a wall of black steel moving through coal country. And when it passed, the ground shook. The weight was not just dramatic. It had consequences. Track inspections were required after many runs to check for damage caused by the locomotive's weight. That is the Allegheny's real signature. It did not just run on the railroad. It made the railroad check for injuries afterward. Power alone does not get the final word. Scale does. The Union Pacific Big Boy was built because helper engines were not good enough. That was the mission: move enormous freight loads over the Rocky Mountains without needing extra locomotives to help shove the train over the grade. Built by the American Locomotive Company and unveiled in 1941, the Big Boy used a 4884 configuration with 4 high-pressure cylinders. It produced about 7,000 horsepower. Not the highest horsepower in this list. That belongs to the Allegheny. But Big Boy wins on total scale. Fully loaded, including the tender, it weighed more than 1.2 million pounds, or 548 tons. More than 1.2 million pounds on rails. Not sitting on concrete, not resting in a yard, rolling on 2 strips of steel through mountain country. It measured over 132 feet long, stretching across the track, with fire, water, coal, wheels, rods, frame, pressure, and mass packed into one machine. Its articulated design allowed it to handle curves despite its size. Without articulation, Big Boy would have been another overgrown fantasy fighting the railroad. With it, the locomotive became usable mountain power at an absurd scale. And despite weighing 548 tons fully loaded, Big Boy could hit 80 miles per hour or 130 kilometers per hour. That number feels wrong. A machine that heavy should not move with that kind of speed. But Big Boy did. Only 25 units were built. Most were retired by the late 1950s. But in 2019, Union Pacific restored number 4014, bringing Big Boy back to life. During World War II, Big Boys moved tanks, supplies, and troops across the country, running thousands of miles each month. They were not built to look good in a catalog. They were wartime workhorses, built to move national weight across brutal distance. Union Pacific needed a locomotive that could make the Rocky Mountains less expensive to cross. So, it built one heavy enough, long enough, and strong enough to make helper engines look like an admission of weakness. 9 locomotives. 9 different ways to push steel past its comfort zone. 1 chased speed. 1 survived the desert. 1 was defeated by geometry. 1 arrived with 2 V16 diesel engines. 1 made the railroad inspect itself for damage. And 1 came back to life weighing more than 1.2 million pounds. Which machine would you bring back at full force? The 611 running away from a helicopter, the yellow diesel wall of the DDA-40X, the track-punishing Allegheny, or Big Boy breathing fire over the Rockies? Subscribe to MEGAMASS. The next machine will not be built for normal scale.